Welcome to the afternoon sessions, everyone. Please welcome Robert. He's going to talk about Panfrost.
Thanks. Yeah, I'm going to talk about ARM GPUs and the new driver for them called Panfrost. It's one of two drivers. Panfrost is targeting the current, I guess, and former high-end GPUs, but we'll get into more of that. So first, a little bit about me. My name is Robert Foss. I live in Berlin. I work in the graphics domain, doing all kinds of stuff. It takes me throughout the entire stack, from the kernel to applications that don't work. When I don't do graphic stuff, I do terrible electronics. This is an earring that doesn't quite work. It's fantastic. It's really annoying. I also do circusy things when I'm bored, like spinning firepoi. It's really fun until you smack yourself in the face. Then it's less fun. And just to preempt some questions, yes, I am named Foss. And no, it doesn't have anything to do with software. It's my mom's last name too, and she does not do software. In fact, I do her software, so yeah. But let's get into it. ARM GPUs. ARM has a lot of GPUs from the very low end to the high end in the mobile and embedded space. And only some of them are targeted by Panfrost. So if we start with their first GPUs, it's the Mali 23400 series. It's codenamed Utgard, and it's supported by another open source driver that's also very new. That's called Lima. This hardware supports up to OpenGL 2.0, and this hardware was actually acquired by ARM when they bought a small Norwegian company called Phalanx. These GPUs are, they're targeting old versions of OpenGL. They're also very much targeting like low performance scenarios. So they're physically very small on an SoC, which means that they're cheap to build. They're also like really cheap to license, probably in the order of a few cents, depending on your configuration. The next architecture that ARM actually designed in-house is called the Midgard architecture. It's the T series of GPUs. It's what the Panfrost driver has been developed against. It supports very recent versions of OpenGL, up to, or OpenGL ES rather, up to version 3.1, and up to Vulkan 1.0. Not all versions of this hardware supports this. There are, I think, 3 or 4 generations of the Midgard architecture, and they've sort of added features to the hardware during the development of those generations. And this hardware was developed with OpenCL in mind, which means that it has a lot of like ALUs, for example, in the compute core. Fun fact is that ARM decided to sell the OpenCL driver like separately from the rest of their software package, which maybe explains why you've never seen OpenCL in a phone. Maybe you have. I haven't. It's not really a thing. The current high-end ARM GPUs is the Mali G series. And it's also supported by the Panfrost driver. It's not well supported. It's sort of on the roadmap. But much of the hardware is similar enough to the Midgard series that you can support it with one driver. So we're going to. It supports later versions of OpenGL ES and up to Vulkan 1.1, which I believe is the latest one. And it's a partial redesign of Midgard. It's targeting a higher performance per watt, like every iteration of this. But they changed some fundamental parts of the GPU. So instead of having a very long instruction word-based compute core, they switched to scalar. So this means that your shaders are being run in warps or thread groups or closures, depending on who you ask. There's different nomenclature. And that's actually exactly how desktop GPUs work as well. These Bifrost-based GPUs, they have a warp size of 4 to 8. Like the first generation was 4, and the later one were 8. Whereas desktop hardware from NVIDIA is 32, and AMD-based hardware is 64. So if you're not familiar with the concept of warps, it's only tangentially related to this talk. But it means that all of the instructions in a shader are executed for a bunch of different threads in lockstep at the same time. So there's one program counter, and you just run through each instruction for like 4 or 8 or 32 different threads at the same time, which works really well as long as you don't hit any conditional branches where the threads diverge. Then it's not so much fun anymore. So don't put branches in your shaders if you can avoid it. Then there's the very latest generation of hardware. You can't really get a hold of it yet. It's codenamed Valhalla. It supports all of the latest and greatest standards, so OpenGL ES 3.2 and Vulkan 1.1. And it has a new instruction set architecture and a redesigned compute core. So exactly what that will look like in terms of writing drivers is not really known yet, because there's no hardware for non-ARM people or to use. So maybe if you're Samsung, you have some hardware laying around, but most people are not. A change from the previous version of this architecture, or version of the hardware, was the warp size, which was doubled to 16, which is pretty close to what desktop hardware use. So you can see the trajectory of getting closer and closer to desktop hardware designs, architectures. So if that's the hardware, let's have a look at the actual driver. Up until 2017, there was no credible driver or no credible way forward for targeting or for supporting the Midgard and Bifrost GPUs. There was not a lot of information out there. What was out there was a kernel driver from ARM that didn't live upstream. It was not upstreamable, or it was not acceptable by the community standards, partly because there didn't exist an open source upstream user space driver for it. So since there was no user space implementation for that hardware, the kernel driver could not be merged. I think there were some other reasons too, as for why it couldn't be merged. Up until recently, you've been stuck with proprietary drivers on old kernels. I think ARM offers like 5 years of support, as far as I know, for their BSPs and drivers, which is problematic for a number of different spaces, like the automotive space, for example. Like if you have an ARM GPU in your car, like what happens after like 6 years and there's a bug? Like, do you really want to have your web browser crash your car? Probably not. This is where the Panfrost driver is kind of interesting, because if you are a hardware developer, you need and depend on being able to support your hardware for a long time, and sometimes longer than ARM is supposed to do it, or willing to do it. I guess unless you pay them extra money, that would probably help out. This is what the reverse engineering tale has looked like. It started in 2017 with a few people. It was Liud Paul, Alyssa Rosenzweig, and Connor Abbott. And it started first with some tooling. So the very first tooling that was produced was the Panfrost shader loader. And the way that worked was you used the ARM kernel driver that was an upstream, and then you used the ARM proprietary compiler to generate a binary from a shader, and then the shader loader submitted it to the ARM kernel driver. And that worked. Like, you could do things, which meant that you could get an idea of what job submission, that kind of stuff looks like. So as with almost all reverse engineering, it starts with tooling and trying to figure out how the hardware actually works. So the Panfrost shader loader was one part, but the process in general has been much about like doing a thing, having it explode in your face, and then inspecting the differences between what the proprietary driver does and what you're doing, and then trying to figure out what's actually going on here. And it's very iterative. You get to one issue, fix it, and then to the next. So Jude, Paul, they started doing the tooling, and Alyssa has been sort of leading this effort, which is kind of amazing considering that she was like I think 16 when she started this work, and I did not do useful things when I was 16. I can promise you that. And Connor Abbott has been doing reverse engineering of the ISA and the compiler. So the ISA for Midgard and Bifrost it's fully documented, and you can have a look at it on freedesktop.org, I think. So with this reverse engineering in hand, the real like upstreaming part of the project started. And in 2019, the Panfrost kernel driver and the Panfrost Mesa driver were both merged. And initially, this was targeting the Mali T860 GPU, only because it happened to be easy and cheap for us to use. So if everyone can have the same dev board, it's sort of easy to not have to do the same like bring up work for a million different boards for no particular reason. So the Mali T860 is where we started. And this is where a few other people joined in on helping out. Tomeo Vizoso did WinSys and Mesa work and kernel work. Rob Herring did kernel work. He used to work for Linaro, but then ARM hired him, which made it a little bit difficult to continue working on the ARM GPU kernel driver, paradoxically. But since then, ARM has been helping out with kernel driver development as well, within certain constraints. So they're not fully on board, as far as I know, but a little bit on board. Exactly what that means is something I can't really answer, but if you find an ARM guy, maybe you can just ask him instead. So that brings us to what Panfrost is like today. And there are a few pieces of hardware that are well supported. The Mali T860 GPU was the first one, due to it being shipped in the Rockchip RK3399 SoC, which is very well supported upstream, mostly or largely due to it being shipped on a bunch of Chromebook devices. So Google has been doing a lot of work upstreaming support for this, which is super appreciated. It's nice to have something mostly just work. And you can run a normal desktop on top of like an RK3399 based SoC. It just works. I brought up Debian and Wayland myself. It really just works, which is nice. Currently, the support for OpenGL ES is limited to 2.0, which is very old. But thankfully, a lot of projects use it as the lowest requirement for their software. So while no one's happy to implement something that's OpenGL 2.0 based, it is oftentimes something that people have to do, especially due to old hardware like the Mali 23400 series of GPUs, which don't really support anything newer. If you want to be able to run Wayland or Weston on top of that, you really need to support ES 2.0. So OpenGL ES 3.0 is on its way. We're working on it, with 3.1 and 3.2 also coming, but we're not quite there yet. And Vulkan work is not started yet. And that's because the Vulkan driver is quite separate from the OpenGL driver. Like, Vulkan is very low level, so each of the drivers are very different from each other, which means a lot of code or there isn't a lot of code reuse between the different drivers, which means that if you are going to write a Panfrost Vulkan driver, you have to start pretty much from scratch. It's not that it's impossible, but there's a lot of work to be done, and you sort of have to prioritize it. And if you want to write a Vulkan driver, now's a good time to start if you're interested. Another note that I haven't actually added to the slides is I just today, this morning, booted Android on the Panfrost driver for the first time. There are a lot of bugs. I got to the boot animation, and that's about as far as we are currently, but it's like a work in progress. And conceptually, it should work. Practically, it does not work quite yet, but I'm working on it. This is where this talk is going to take a little bit of a turn and look into what a driver actually looks like. So we've talked about Mesa and the kernel, but there are many parts to it. And in Linux or graphics open source, that means a lot of different code bases. And we're going to have a quick look at what that looks like, that landscape. So there's the user space and the kernel space. The drivers for graphics chips are huge, and you really, really don't want it all to live in the kernel. Also, you have to expose APIs that really wouldn't be suitable to expose through the kernel. So what you do is you split the graphics driver into two parts and then have them communicate with each other. The bottommost part is the kernel part. It abstracts the hardware for us. And the graphics drivers live specifically in the DRM subsystem, the Direct Rendering Manager subsystem. And they handle, or the drivers there handle GPU and display hardware, like memory allocation, interrupts, GPU job submissions, that kind of stuff. And on the user space side, there's Mesa, and Mesa does a lot of things. It's really a rather big code base, but it compiles shaders, it builds command streams, and it submits jobs to the kernel. That's like the rough gist of it. And Mesa supports a lot of different GPUs, and a lot of the code is shared between these different drivers, which is really where the power of Mesa is at. You get a lot of different teams looking at shared code, which means that it's going to be reasonably well supported and stable and well tested. If we're going to take a little bit of a deeper look, there's also libdrm, which is a library for accessing the DRM subsystem. It's basically just a wrapper around the DRM subsystem. It makes it a lot more convenient and pleasant to interact with the DRM subsystem. Like doing everything through ioctls is fun and all, but it's not that fun. And if you can avoid it, you can just save yourself some pain. And libdrm also prevents a lot of re-implementations of these normal access patterns. So it's also another code base where a lot of sharing just happens because the code is just shared between different drivers to do the same things. If we look closer in Mesa, there's what it actually does for us. There's the APIs that the end user uses. This is, for example, OpenGL and Vulkan. There are other things like OpenVG and OpenCL, maybe one day, if we're very lucky. So a lot of code is shared for the different drivers for OpenGL. That's not necessarily very true for Vulkan, like I mentioned before, since a lot of the Vulkan implementation is hardware specific, which means that it's hard to share between drivers. And on top, we have the applications, of course. That's the good stuff. The only thing that really matters to our users. So I thought I'd throw it in there. But let's have a look at Mesa. Mesa does a lot of things, and I'm not going to talk about all of them. Some of them are boring. Some of them are needlessly complicated. But I'd like to give you an idea of what some of the large parts are. And maybe the biggest part is Gallium. And Gallium is a driver writing framework. Almost all of the drivers are based on Gallium. There's one driver for Intel hardware that's being replaced currently that doesn't use Gallium. And that means that a lot of code can be lifted out of like the actual hardware-specific drivers and into this shared framework, which means that it's very well tested. It's very performant, and as Intel discovered recently, when they decided to switch from their non-Gallium driver to a Gallium-based one, there's a lot of like actual performance wins you get for free just by using the Gallium framework. It does a lot of heavy lifting for you. And if you take a step back, it's also a part which really allows vendors to cooperate with each other. So that's a nice sort of community benefit to it. But in practical terms, this is what Panfrost is built on top of. There's more parts to the Panfrost driver, but Gallium is the driver framework that is built on top of. Gallium also has other parts to it, like WinSys or the window system. It basically allows you to set up and allocate buffers from the kernel. This is also very like hardware specific. So each driver has a WinSys implementation, and it basically just talks to the kernel and sets up buffers, and that's all that it does. But it's code that can't really be shared entirely between all of the different drivers because the hardware has different quirks and operates in different ways, and yeah. So there's a Panfrost WinSys. But there's more than Gallium in Mesa, and another big and interesting part is the compiler infrastructure. There's a compiler framework in there. It's used by most of the drivers. The Radeon SI driver used LLVM until recently. Recently, Valve published a new driver, or sorry, a compiler for the Radeon SI driver. It's called ACO, and it outperforms the LLVM-based one. Using LLVM as a GPU driver is kind of problematic because it compiles things while you're running your application. And LLVM is slower than what you'd want a GPU compiler to be. It also isn't at all targeting that use case, really, so it's not surprising that it is. But it creates some issues. It's also kind of a messy dependency to have in a project. Like, let's say you're building Mesa inside of Android. Now you have to pull in like LLVM and make sure that that builds on Android, which is not fun or enjoyable for anyone. There's also parts of LLVM that's sort of used for different things, like OpenCL support in Mesa is not entirely there yet, and LLVM is partly, or can be used to enable that through the SPIR-V IR support it has. If we look inside of the compiler, there's an important part is the NIR, intermediate representation, or new intermediate representation. It was written by Connor Abbott, also when he was ridiculously young, young enough to make you feel bad. It's SSA-based, which means that, yeah, just to give you a short, like a small idea of what SSA-based means, it's sort of, if you imagine a code base where every assignment or every variable is only assigned once. And if you have like loops where a variable is assigned to multiple times, you deal with that and you sort of create a copy of that variable every time it's assigned. And it's what most modern day compilers are based on. And because of that, there's a lot of research into this space. So compiler optimizations are oftentimes implemented on top of an SSA-based IR format. And the NIR IR supports or implements a bunch of optimizations that you sort of get for free when you base your compiler on top of it, like dead code elimination and common sub-expression elimination. There's also a bunch of other optimizations that it implements, which is nice to not have to implement for every single driver. So NIR is sort of the middle end of a compiler. there's the compiler. The terminology is really dumb. There's the compiler front end, which is like implementing a language like C or whatever and parses it. There's the middle end, which does things. And then there's the back end, which handles like hardware-specific things. So NUR is definitely in the middle end. And on top of it, you build your back end for your hardware. So in this case, there's the Panfrost back end. That's sort of slightly untrue. There's actually two back ends. There's the back end for the Midgard architecture, and then there's the back end for the Bifrost architectures. They're slightly different. Like I mentioned before, there was a switch from scalar to, from very long instruction words to scalar between Bifrost and Midgard. So the compilers really have to be different. You can't use the same one. Taking a step back and looking at this from a very high-level overview, there's a question of who actually contributes this code. And if I'm going to give you only one answer, it's going to be Intel. But also there's a large community, and a lot of different companies contribute. If you look at the short log to the left, that's the contributors for the kernel, and to the right is the contributors from Mesa. And there's a lot of Red Hat folks, Intel folks, VMware folks in the top of this list, but this list has a very long tail, so it's not all about like the top contributors. But Intel definitely dominates this, partly or maybe largely because they've been a member of this community for a long time, since 2009. And that's way before anyone else was publishing open source drivers, or way before any vendor was supporting these drivers. So that's a large reason to as for why. Also, I'd like to talk about how contributions work for the graphics space. There's the kernel, the normal kernel procedure, which is mailing lists for everything. And Mesa uses mailing lists as well, and up until last year was mailing lists only. But somewhat blasphemously, in the last year, Mesa has been partly GitLab based. Like you can use the mailing list in the same way you always have, and that's fine. But you can also submit code through GitLab and have discussions there. So mailing list submissions are still allowed, and the mailing list is maybe changed to be more discussion focused. There's also the RSC channels on Freenode it's called DRI Devil, and that's also where a lot of the conversations happen about stuff. Another thing related to this is continuous integration. Kernel CI has been, I'd say it's rather established by now. Mesa CI is a new thing. It doesn't quite exist yet, in that we're working on it. When you submit a merge request on the Mesa GitLab, it will be tested, and the tests will be based on the software-only drivers. So there are software drivers which obviously don't require any specific hardware to be used, which makes it relatively easy to integrate into a CI pipeline. So every single patch submitted through GitLab will be tested. I mean, that's not super helpful if you're working on hardware-specific code. But the plan is to extend this infrastructure to support hardware as well. But it kind of requires a little bit more infrastructure and people running actual hardware labs, because hardware is bad and it will break on you, and someone needs to be responsible for it, essentially. That's everything I had to say about Panfrost. And if you have any questions, just, ask me.
Does anyone have any questions? Well, let's give Robert a big round of applause.